Good morning, happy Friday. What a way to start your Friday with some stats. Okay, so we are going to, yeah. Oh yeah, and you've got a test, right? So the test will be available at 9 BC time. And then, so you can do it whenever you want. It's going to be a time test, so you'll only have 80 minutes, okay? And it should say somewhere on there, right? But make sure that you do the test at some point, right? Maybe take some time to prepare yourself. Remember, it is long. It is on the long side. I cut it down. I think it's at 15 questions now, but some of them are a little bit longer, so that's why I cut it down. So the test, right? Make sure that you keep your pace up. Okay, so test number 2 will be available after class. And there's instructions for the submission, 14 multiple choice kind of short answer questions, and then 1 long question. Yeah. So test number 2 will be available after class. And it's an 80-minute timed quiz. I tried to set it up so that you just have to submit at the end, because that was really weird with test 1, how I think you had to submit every time. I tried to make it so that doesn't happen. See if I succeeded on my end. It looks like I did, but who knows? So it's going to be, I'm pretty sure it's 14, or I guess the first question is the long answer. And just to clarify, it will be worth 13 marks. Okay, but you won't get those 13 marks. So your grade is going to look low when you submit it, because I've made that question worth 13. Okay, so and there's nothing to get marks for. So you're already missing 13 marks because you have to submit your answer, your long answer. And then there's 14 questions that are short answer. And the total is going to be 65 marks. So whatever that is, 65 minus 13 is 52. Right, so the initial submission, just so you don't have a panic attack, is out of 52, right? Not 65 like it says, okay? And then I'll add the 13 depending on your long answer. Remember, you have 10 minutes to submit your written work. And I made it the first question because I want it to be first in your work that you submit, so I don't have to scroll through a bunch of random questions to get there. So that's by design. So make sure you have your first question as your long answer and then have your written work. And it's worth a lot of marks, right? So you'd want to focus on your long answer and make sure that you've covered all your bases. It might be a little intimidating to see right away, right? But usually there's clues in the rest of the test as to what you should be doing for the long answer. So maybe scroll through it and I don't know, you know yourself better for testing. Okay, so it's open for 80 minutes. So once you start, you have 80 minutes. You only get 1 attempt, okay? And then it closes at 11:59 on PST on Monday. Okay, so you've got time, so you can work through it, right? Carve out some time to do it, and then yeah, it'll be good. If there are any questions, you can throw them in the chat, but otherwise, we're gonna talk more about numerical data. So we've talked about one sample mean? How do I compare it to a hypothesized value? Then we talked about two samples. There are two ways that we could have two samples. They can be paired or they can be independent. All three of those use a t-test, right? And so today, what I want to talk about is what if we have more than two means that we want to compare, right? So, you know, it's not unreasonable to think that we have three groups of something, right? And so we want to compare, maybe if we even look at letter grades, then we have tons of groups, right? A plus, A minus, B plus, B minus, et cetera, et cetera, et cetera. And then maybe how much time people spend on homework or something like that, right? And so, so we could do comparisons across more than two groups. And to do that, we need to use an Anova. Okay, and so today, I'm going to bump it down one line. I forgot to mention one thing. 7.5 is on an Anova, which is an analysis of variance. That is what we're doing, but I know initially it doesn't really make sense when we call it an analysis of variance, because what we're doing is actually to compare multiple means, to compare many means, right? Or more than two means. Okay. So we use an Anova, and what's interesting is just like a t-test, we could use an Anova for other scenarios as well. And so this is the one that we start with, and then we could apply it to slopes and things like that. So once we've introduced an Anova, then we can apply it to different scenarios, right? So just like the t-test, just like the z-test, just like the chi-squared, right? So all of these have some flexibility. One thing I wanted to mention is that I am going to skip 7.4, which is on power calculations. I won't have it on the test. I encourage you to read it on your own time, but I'm not going to test it. Okay, so here, 7.4 is on power calculations. Okay, so read on your own. And maybe I'll need one more line here. Maybe two for space reasons. There we go. But will not be tested. All right, now we're talking final exam stuff. Right, so the power calculations will not be on the final exam. They're good for if you're heading out into the field, then you know you should be aware of power calculations, but I'm going to skip it because I want to. No, because I prefer, we need to talk about Anovas. So, so what the Anova does is if we have multiple groups, then what we could do in theory is we could do pairwise comparisons, right? If we have, you know, three groups even, right? Consider three groups. Okay. If we want to compare the means, we would do how many comparisons, right? I would compare group 1 and group 2. I would compare group 1 and group 3. And then I would compare group 2 and group 3, right? So here I would have to do 3 different comparisons. Now imagine if you have 4 groups, right? Group 1, group 2, group 1, group 3, group 1, group 4, and so on and so forth. And you'd have to consider all those different situations. But every time that we do an individual test like this, then we're introducing the possibility of being wrong every time. right? So if we use an alpha level of 0.05, right, then there's a 5% chance that we're wrong, right? There's a 5% chance that this difference that we saw was just due to random chance. Okay, so when we boil it down and just look at individual pairings, which we will do, but we don't want to do that initially. Okay, and so we could consider the pairwise comparisons, but at alpha equal to 0.05, right, depending on how many different group pairings you have, right? So even at 20 different pairings, and it doesn't take that many groups to get there, then you're going to see one difference just due to random chance, right? And so we introduce a 5% chance of seeing a difference, right? A significant difference by just due to random chance. Okay, so that's not good. So what the Anova does is it considers all of the means together as one group. Well, I shouldn't say group because groups mean the different categories, right? But so each of the means together, and how I imagine it is it kind of peers into a box like this and goes, hey, is anyone different in there? And then from the Anova, which runs an F test, and I know it gets boggy here, right? But so we do a hypothesis test, and if that hypothesis test is significant, right, which means that we can reject H0, that's a significant test, then we say that there is some mean in there that is different from the other, at least one that's different than the others in there. Okay, and so instead, we should run an Anova which considers all means at the same time, and a significant test means that there is at least one mean that's different from the others. It doesn't tell us how many, it doesn't tell us which ones, but it's, so imagine before computers were doing all this work for us. So imagine you have to compare all these means. Let's say you have 5 different groups. You can imagine all the different pairings that you'd have to consider. And then you'd have to make adjustments based off of that. And then you don't want to set out and do that only to find that there's nothing going on, right? And so that's why the Anova was developed, is one, to avoid having to do all those pairwise comparisons, but also so that we can just have a quick check-in and say, hey, is there anything worth finding in here? If no, then we put that away, right? We would stop there, right? So you could save some time. Okay, so we should run an Anova which considers all means at the same time. And if the test is significant, we know at least one mean is different from the others. Okay. So this at least one mean is different from the others we won't know which one. Yet, nor how many, right? It just says at least there is something in here that's different, okay? Nor how many means are different. From each other, I should add. Okay, let me add a page here. Okay. So in general, an Anova is a hypothesis test. An Anova is a hypothesis test. And the null hypothesis, how can we summarize? Okay, so I want to see if there's at least one mean that's different. Okay, so then our null hypothesis is going to be that they're all the same, right? All the means in here, mu1, mu2, mu3, mu4, blah, 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 up to mu k, because we're going to say we have k groups, is they're all equal to each other. Okay, so the null hypothesis is that mu1 is equal to mu2 is equal to blah, 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 all the way up to mu k, because we're going to say we have k, k groups. Okay. If they're all the same, that means there's nothing going on, right? So there's no differences anywhere. They're all insignificantly different, right? They don't have to be exactly the same, right? We've seen that, but there is some wiggle room where we say, okay, well, that's actually not significantly different. So our null hypothesis is that all these means are all the same. Now, it's hard to summarize that at least one is different from the others. And there's lots of ways that you can do it, but I actually prefer just the word version. And so the written version, because if we use symbols, we end up using things like mu I does not equal mu j for all I and j, and it gets really messy, right? And so at least one mean is different says the same thing, and I think that's easier. So at least one mean is different. Okay. There are some conditions that we have to satisfy before we can run the Anova. Okay, and so we need to check / argue, right? Sometimes we have to argue these assumptions because that's what the assumptions are. If you're running an Anova, then you're telling me that you have made these assumptions. So you have to put that down on paper, right? And so sometimes it's not obvious, but you would have to say, okay, and here's another thing I'm assuming, right? And so we need to check 3 conditions before running an Anova. The first one is that the observations are independent both within the groups, but also across the groups. Okay, so what that essentially is saying is that all our observations that we're considering here, they have to be independent of each other, right? So we can't have things like you have to have a qualifying trait to be in some group, because then you're not independent of each other, right? And so the observations must be independent within and across groups. Within and across groups. That's easily done. right? We've seen that before. If the sample was randomly selected and then we split into groups, then that would satisfy this independence condition, right? And so our first check would be if they're randomly selected. If they weren't, then you'd have to assume that these observations are independent, both within the groups and across the groups, right? So either way, you have to say it. The next condition is that the data within each group has to be nearly normal, right? So approximately normal. So we check the data in each group, and we have to make sure that we have an approximately normal distribution. Okay. So the data within each group are nearly normal. And then the third condition, because the second and the third condition, we can usually get away with checking with some side-by-side box plots. So I'll show you what that looks like. Okay. But the third condition is that the variability in each of the groups is roughly equal, right? So we can't have a group with a super small standard error, standard deviation, right? We can't have one group that has really small spread and one that has really large spread, right? And so we have to assume that we have this constant variance across the groups. So the variability across the groups is about equal. Okay, so I'll show you some of the things that we can check here. But in general, these two conditions, we can usually check these using side-by-side box plots. Okay, remembering that if you have roughly even spread around the median, then you have a normal distribution, right? Because then, your quartiles are nice and evenly spaced out. And so a roughly symmetric distribution around the median means that we have a normal distribution. Remembering that a roughly symmetric distribution around the median indicates a normal distribution. Indicates a normal distribution. Usually. There could be like a weird case where you do have, because as long as the distribution is symmetric, right, then you would see that symmetry in your box plot. But you could, so here I'm kind of guarding myself, because you could have a bimodal distribution that's perfectly split across the median, but that's rarely going to happen. And so, so usually if you have symmetry in your box plot, then you're safe. Okay, and then of course, so that's the normal portion, and then the variability, as long as our box plots are roughly equal in width, then we have roughly the same variability. Okay. And you know what? I want to break this up a little bit more here. How about this? normality. And then the variance or the variability, just so I break it up a little bit. Roughly equal spread in each of the box plots is an indication that we have roughly equal variation or variability. So equal, maybe I'll say roughly equal. Depending on our sample sizes, right, we can be a little bit more flexible for small data sets because those box plots aren't going to look that good. But small data sets bring their own problems. And so we love to have large data sets. But roughly equal spread in each of the box plots is what we're looking for. Okay. So the Anova, we usually, so kind of old school is making you calculate the Anova. I'm not going to do that. I'm going to give you output, but first I want to talk about what the output is. Okay, so an Anova generates a table right from software that we need to be able to interpret. Add a page here. Yeah. So if we have a total sample size of n, okay, so the total sample size across all groups is going to be n. Okay, and the number of groups that we have, number of groups or means to compare is going to be k. Okay. So then an Anova, and I'll show you some output I stole from the textbook here, but an Anova is going to have the following setup. And maybe I should start here. Okay, so it's going to be kind of a long table here. And remember, you're going to be given this output, so I don't want to spend any time talking about how we got here. Even the textbook kind of glosses over it because it can become quite kind of technical and pretty math heavy. So, but we just apply the Anova to our data set, and then we're happy with that. Okay, and so what it's going to break up is it's got the group component. Okay, and sometimes we call this the within, I want to say, or is it between and within? Anyways, maybe I should skip that because I can't quite keep them straight right now. That's okay. The group and then the residual, which is often called the error term. Right? And then it's possible to have, I want to change my line type. So it's like, it's usually not part of the output, but we could have some total here. Okay, which for some of these columns is just going to be the total of the top two rows or the rows above. Okay. Oops. So each of these two rows are going to have some degrees of freedom. So F has two parts as its degrees of freedom. It has a degrees of freedom for the group and a degrees of freedom for the error. Okay, and so what we're going to have is the degrees of freedom with a little subscript G. which is going to be k minus 1. And then we're going to have some degrees of freedom, which is, we'll put a little e on there for the error. I don't like to use r. And that's going to be n minus k. Okay, so that's why we had to establish the n and the k's, right? Because those are the ones that we need to, those are probably the only calculations that you need to be able to do. Okay? And then everything else just kind of flows. So then, of course, the total degrees of freedom would be k minus 1 plus n minus k. If you think about that, k minus 1 plus n minus k, well, then I'm subtracting k from each other, and then I have n minus 1 as my total degrees of freedom. But I'm going to leave that here. Let's see here. Oh, maybe not, n minus 1. Okay. The next column is going to be the sums of squares. And this is where I'm totally just ignoring math altogether, and you're going to just have it. Okay. And so we're going to denote this as the SSG. So for the groups, and then the SSE. And then if you add those two up, you have the SST. Okay. We're not going to need these totals, so usually they're not included. Well, we won't. Some people do for other things. Okay, so then we're going to talk about the mean squared. So MS, we can have the MSG, which, as long as you remember that it's the SSG divided by the degrees of freedom G, so it's this second column divided by the first column, right? And same thing with the MSE. The MSE is the SSE divided by the degrees of freedom for the error. So that's SSG divided by the degrees of freedom for G. And then the MSE is the SSE divided by the degrees of freedom for E. Right. So here, I just want to highlight that this came from here, and this came from here. Same thing with the other one. This came from here, and this came from here. I don't know if that helped or hindered. Guess we'll find out. So once you have your mean squares, and I'm going to ignore putting a total mean squareds because we never use it. And so the F, and F, I'm going to clarify, F has 2 degrees of freedom, as in 2 components for its degrees of freedom, not just 2. It's got, DFG degrees of freedom, and then DFE degrees of freedom. Yeah. So F is going to be the MSG divided by the MSE. And then it's going to give you a p-value, which is from software, because I'm not going to give you a table. There are F tables that you could look up, but they use the critical value approach. So it's going to give you, you feed it the degrees of freedom that you have, and then it's going to return an F value that you have to compare to your F value. If your F value is larger than that point, then you have enough evidence to reject H0. It's going to be a lot easier to just use the p-value from the software. So that's what I'm expecting of you. But this, you do have to be aware of the anatomy of an ANOVA, right? You don't want to just, well, ultimately, we will just be looking at the p-value, and then that's going to help us determine if we can reject H0 or not. Right, and the p-value, we use it the same as all the other p-values that we've seen. If it's less than 0.05 or some other level that we've predetermined, we can reject H naught. Okay, so let's see here. I'm just going to steal this example that we had in the textbook because it runs through all the different things that we can consider. Okay, and so right, we've got multiple offerings of the same course, and this happens at the College of, it happens everywhere, right, where we have multiple sections that you can choose from. And so what we're interested in here is, are there any statistically significant differences in the first exam scores in the three classes A, B, and C, right? So we've got three groups and we're analyzing the mean exam score, first exam score. Okay. So as soon as we have more than two groups, right? If we only had group A and group B, and we wanted to compare those means, we could do that. We could do a 2-sample t-test and then we'd be good because it's a 2 independent samples t-test and we know how to do that, right? So, but here, because we have 3 groups, now we have to run an Anova, okay? And so the only part that you need for your null hypothesis here, they've written it out in words, that all the average scores are insignificantly different, right? And so they're all basically the same, and how we denote that is mu A equals mu B equals mu C. Okay, that's our null hypothesis for the F test, right? And so this is why we call it an F test. So an Anova runs an F test, I'll say. Okay. So the F test is going to tell us if anything is going on in there. Okay. And then the only thing that we need for the alternative hypothesis is really that the average score varies by class. We don't know which one, but we would need to dig deeper to figure out which one is different, or maybe, well, with 3 cases, there's going to be one that's different, at least. So, okay, so we've got our null and alternative hypotheses. Now let's consider the conditions before we actually run the test, right? And so the conditions, the first one is independence. And there's no reason to think that that people are choosing classes. Maybe they are, but let's just, because we have to assume that all these students are independent of each other, right? And so they were independently choosing classes and they were independent of each other in the classes. That's not necessarily true, right? You have friends and you want to take courses with your friends and you know, read Rate My Prof or whatever. And so that's not necessarily true. But it is something that we have to assume before we go ahead and do the test, right? And so even if you feel yourself saying, oh, that's not really true, then talk yourself out of it. Okay, so for the independence, it is reasonable to assume, that's my go-to line. No one can argue with that. It's reasonable to assume all students are independent of each other. Within and across classes. And we say that because we have to say that. The second condition is the normality condition. And what I have some summary information here that we can look at. Okay, so the normality condition, if I look at these box plots, they're roughly symmetric around the mean, or sorry, around the median. The line is the median, right? And so even this group C, even though it's a little bit squished up top here, if I kind of take my fingers and I measure it, it's not that huge of a difference. Okay, so the box plots are roughly symmetric about the median. Okay. And the third condition is that constant variability. So the variability condition looks like the width. So now I'm looking at the total width of the box plots from the maximum to the minimum, or the whiskers, typically. If you have a large data set, you're allowed to have a couple of outliers, so that's okay. But we usually just look at the whiskers. Okay, so the width between each whiskers is roughly the same. Okay, so each box plot has roughly the same width. Okay. We can also confirm it by checking the standard deviations across each of the groups, right? And so we also see that the standard deviations are approximately equal. We also see that SI is approximately equal across the groups. So that's good. Okay. Delete that. I don't really need that. All right. So therefore, conditions are satisfied. So we can go ahead and we can do our ANOVA or our F test. Right, and so here we have all this information. So the lecture is the group, right? Which group are you in, A, B, or C? And remember, we have 3 groups, so 3 minus 1 is 2. That's good, it all checks out. And I can check here, I have a sample size of 58, 55, and 51. So if I add those up, I get 164. 164 minus K, right, is, so K is 3, is 161. It's all checking out, right? And so we get these sums of squares, we get the mean squares, we get the F value, but really the only thing that we're interested in here is the P value, right? So we kind of skip straight ahead to the P value. For the F test. As with any other p-value, right? If we have a p-value and it's less than 0.05, we haven't said any other alpha level, so we'll use the default. So then, since the p-value of, and usually I like to show off what it is, 0.0330, it just helps support your statement, right? So since the p-value of 0.0330 is less than the assumed alpha level of 0.05, we have enough evidence to reject H0. We have enough evidence to reject H0, right? And that's in favor of HA. In favor of HA. What does that mean? It means that there's at least one group that has a different mean, a significantly different mean than the others. So therefore, there is at least one group with a mean that is significantly different than the others. That's great. You wouldn't want to leave it there though. That'd be bad. Right, so now the question is, okay, so the follow-up question here, so after we run an Anova, and find a significant result, which means we've rejected H naught, right? So when we say a significant result, it means rejecting H naught. So after we run an Anova and find a significant result, we can continue by conducting the pairwise experiments, by conducting, or comparisons, by conducting the pairwise experiment. I keep saying experiments, comparisons. Okay. However, right, when we're doing those pairwise comparisons, remember the problem was, okay, at an alpha level of 0.05, just looking at these pairwise comparisons and doing a series of these tests, well, I'm opening myself up to a type 1 error every time, right? A 5% type 1 error every time. So to avoid that, we use the Bonferroni correction, which is a really funny thing, I think. It's a last name, obviously, so it's not that funny, but it's fun to say, Bonferroni. Okay, so when we do multiple comparisons, which is what we're doing here, right? So when we're testing many pairs, right? So many pairwise comparisons, then what we do is we have to apply the Bonferroni correction. So what we use instead of 0.05 is that we have some new corrected alpha level, alpha star, which is the 0.05 divided by K. Now, the capital K is the number of comparisons that we're doing, okay? And so if there are K groups, then all the possible pairs are compared, and how we calculate that K is K times K minus 1 divided by 2. So for example, if alpha is 0.05 and we have K equals 3 groups, right? Then big K would be 3 times 2 divided by 2. And we saw that, right? 3 different groups. So K, big K is 3, right? And so A and B, A and C, and B and C. Three possible pairwise comparisons. 3 possible pairwise comparisons. So what we would say, with my minute to spare here, not even, I'm all out of time. Alpha star here would be 0.05 divided by 3, which puts me at roughly 0.0167, right? So that's what we would use, but then the test stays the same, right? We would just use this adjusted alpha level. The test, or sorry, the t-test stays the same. Just use the alpha star instead. There, that's the short version of Anovas for testing many means. All right, so if you have any questions, let me know. Otherwise, have a great weekend and good luck on test 2. Stop this here.